The Aspen-HYSYS dynamic solver is different from the steady-state solver. In the steady-state solver, the pressure and flows are not related. In dynamic simulation, the pressure and flows are related. In a real plant, flows go from high to low pressure, and if there is no pressure drop, there won't be any flow. There are numerous relations in literature between pressure drop and flow rate, but the simplest is the turbulent flow equation. The turbulent flow equation states that the flow through a valve is proportional to the square root of the product of pressure drop and fluid density, with a proportionality constant that depends on the exact geometry of the valve and percent opening. When given at 100% valve opening, the constant is called CV. HYSYS supports numerous correlations, such as the Fisher and universal gas sizing equations. Because the flows are pressure-driven, upstream behavior can be influenced by downstream equipment. For example, a blocked valve downstream could cause pressure to build up and affect upstream flows. This is much more realistic, but it also means that the flows cannot be solved sequentially like they are in steady state. Rather, all the flows are solved simultaneously. We must specify the pressures on several streams to fulfill degree of freedom requirements. While not required, it's generally suggested to specify the pressures on boundary streams. For example, take a simple separator with one inlet, two outlets, and valves on each of the inlet and outlet streams. There are flow rate and pressure values at each inlet and outlet, along with a pressure in the separator, for a total of 7 unknowns. Each valve has an equation relating its flow rate and pressure drop, and we can write a differential equation relating vessel pressure to flow in and out of the vessel. This gives us a total of 4 equations. Since there were 7 unknowns, we have 3 degrees of freedom. If we were to specify the boundary streams, we would have 0 degrees of freedom, and the system could be solved. In steady state, there's no accumulation. Flow in equals flow out. In real plants, and hence in dynamics, many unit operations have significant holdup. If more vapor is forced into a fixed volume, the pressure inside the vessel will increase at a rate proportional to the percent increase in moles. If the vessel is small in proportion to the net change in flow, the pressure will increase faster than if it's a large vessel, as the large volume will dampen the changes in flow. It is also possible for the effective volume of a vessel to change. If liquid holdup increases, there will be less space available for the vapor, causing the pressure to rise. In dynamics, vessel rating matters, and it can have a large effect on the performance of your process. In steady state, equipment sizing is not required unless you are modeling a kinetically limited process, like a kinetic reactor or certain types of distillation. In dynamics, it is important to select proper equipment sizes. Equipment sizing will affect holdup, process response time, and pressure drop. There are various types of valves: linear, quick opening, and equal percentage. These correspond to how the flow rate through the valve changes as a function of valve percent opening. A linear valve has linear characteristics. In other words, the flow is directly proportional to the valve percent opening. A quick opening valve obtains larger flows initially at lower valve openings. As the valve opens further, the flow increases at a smaller rate. An equal percentage valve initially obtains very small flows at lower valve openings. However, the flow increases rapidly as the valve opens to its full position. HYSYS allows you to model all of these valves. A fourth option also exists where you can define your own percent CVs for various valve percent openings.